Okay. Um, so in the old approach in choice theory, for example, in Alfred Marshall's textbook, the starting point was to postulate, to assume that the consumer has some utility function, that any consumption bundle gives the consumer some utility, which is some sort of psychic measure, some mental measure, right? Often the unit specified was utils. Now, utility is not like height or weight. Height or weight is objective. We can take a measuring tape or a weighing scale and get a person's height or weight. It's tangible, measurable. Utility in that sense is a nebulous concept, right? We can't look into people's heads and measure how much utility they're getting. These days you have fMRI scans and all, and see the neurons which light up. But certainly in Alfred Marshall's time, that technology wasn't there. So this was just, a kind of an introspective construction that, we feel different degrees of happiness. But it wasn't a very good foundation to a scientific theory of consumer behavior, demand functions, and so on. Because the very object that was postulated, which was assumed, was not something that was observable, which didn't have sort of empirical counterparts. So two economists, John Hicks and Eugene Slutsky, they sort of early in the century, they developed a different approach. And they said that, well, we will not assume a utility function. What we'll assume instead is that the consumer has a preference ordering over various alternatives in her mind. So if a consumer walks into a supermarket, you can create two consumption bundles. One has a certain amount of biscuits, a certain amount of milk, some fruit. Another has those items in different quantities. And you can place those two consumption bundles, A and B, let's call them, in front of the consumer and say, which do you like better? If if we announce a free gift for you, you could choose one of these two. Which one would you choose? And in principle, you can get a response to that. It's a well-defined question, and any answer will also be well-defined and understandable. So these guys, Hicks and Slutsky, they said, let's see if we can, develop a fruitful theory of choice, starting from the assumption that consumers have preference orderings like this over their various choices. And let's see if we can, if we can develop some predictions about market behavior, consumer behavior, and then we can, test whether those predictions hold up against data. So the old approach where a utility function was assumed right away as a starting point is called cardinal utility theory. And the new approach is called ordinal utility theory. So I'll discuss this ordinal approach to utility. And as we go through all of this, remember that the final goal is to develop some testable implications of the theory we are developing, meaning that, it should make some statement that consumer choices will show some pattern which can be tested against data, right? There has to be falsifiable predictions. So the starting point is not even a preference ordering. We can dig deeper and we can say, we'll start with binary relations. We'll start by asking whether, or assuming that between any two alternatives, the consumer can give us, a preference. So something like the bundle A is preferred to the bundle B. That'll be the sort of building block. We'll assume that those kinds of comparisons are there in the consumer's head. Now, binary relations can be thought of in more abstract terms, not just, consumers' rankings, but many other kinds of relations. For example, taller than is a binary relation, friend of so-and-so loves so-and-so, so-and-so hates so-and-so. These are all binary relations, right? It's something which connects two elements. The two elements could be two people, two objects, two consumption bundles, and so on. So at the highest level of abstraction, as I said, we can represent in sort of abstract terms a binary relation as something like this. So X, R, Y is a statement involving the binary relation R. X and Y are two elements from a relevant set. So this is how it's written. Now, depending on which kind of binary relation we are looking at, it may or may not have certain properties. Okay. Just random examples of properties that are often used in set theory and sort of abstract mathematics. One possible property is commutativity. Some binary relations are such that if X are Y, then the opposite is also true, Y are X. For example, friend of is such a relationship, right? But son of is clearly not, if A is the son of B, B is not the son of A. So that binary relation is not commutative. Another possible property could be reflexivity, that X are X. So if I think of the binary relation at least as rich as, that's reflexive. I'm at least as rich as myself. But if I think of this as strictly richer than, then that's not reflexive because I'm not strictly richer than myself, obviously. Last example of a property is transitivity. Transitivity basically says there are no loops or cycles. More concretely, for any three elements, X, Y, Z, suppose the following is true: X, R, Y, and Y, R, Z implies X, R, Z. Okay. If this property holds for a certain binary relation, then we'll say that it's a transitive binary relation. Again, examples, taller than is transitive. Yes. A is taller than B, B is taller than C. It has to be that A is taller than C. But friend of is not transitive. Right? A friend of a friend is not necessarily my friend. So depending on what binary relation we are talking about, we can come up with a list of properties. Now, when we are studying consumer choice, consumer preference, the binary relation we'll focus on is the weak preference relationship. So is the bundle A weakly preferred by the consumer to the bundle B? Right? That is our binary relation that we'll study. And we'll want to impose some properties on the binary relation. Of course, we have to assume something to get any results, right? There's no theorems you can prove without any axioms or assumptions. So the question at the outset is, taking this binary relation, weakly preferred to, what are reasonable properties we may expect it to have for most people, for most consumers? Okay, it may not hold for every consumer, but as long as it holds for most consumers, then it's a good basis for a theory. So what assumptions do we want to make? Or what axioms, assumptions, interchangeable terms. Okay, let's spell things out a little or define things a little further. The preference relation is our binary relation of interest. we're looking at an n good world, n commodities, and they're labeled 1 through n. Okay, xi is the quantity of good I. So we are taking quantities to be continuous variables. Okay, they're all from a continuum. They're not discrete things. That just gives us the convenience, analytical ease. A consumption bundle is basically a vector in n-dimensional Euclidean space, right? The consumption bundle is basically a vector which specifies how much of what quantity of each good is there in the bundle. Okay, so that's just coordinates of any of a point in n-dimensional space. We'll use this symbol, the curly weak inequality, to represent our binary relation. The meaning of it will be at least as good as or weakly preferred to, okay, in the commonsensical sense of those terms. So when I write something like this, what does it mean? There's a very compact way of saying that to the agent understudy, to the consumer understudy, the consumption bundle X superscript 1 is weakly preferred to X superscript 2. Let me just spell out, if you look at closely at the notation that we're using, bold letters will always denote vectors, right? And non-bold normal font will denote scalars, right? So this is just a compact way of writing down a vector, this bold X. And for each individual quantity, for each individual good, we represent which good we're talking about through the subscript, whereas the superscript is a description of a particular bundle, not just the quantity of one good, but a whole vector of goods. So hopefully that is clear. Okay, so let's come to the question of what will be the axioms. But before that, one more thing. There are other preference relations we can think of. One is strict preference and the other is indifference, right? Intuitively, we understand these terms. In this more formal representation, how do we understand them? In the formal analysis, we'll take this to be the building block, right? The weak preference. We can define strict preference and indifference using the weak preference ordering. This is how. When do we say a bundle is strictly preferred to another bundle? Well, if X1 is weakly preferred to X2, but the opposite is not true. When that is the case, we'll say X1 is strictly preferred to X2 for obvious reasons. And if we have a case where X1 is weakly preferred to X2 and X2 is weakly preferred to X1, then we'll say X1 is indifferent to X2. The consumer is indifferent between those. So the strict preference and the weak and the indifference relations are also binary relations, which are defined through the weak preference relation. So we will place our axioms not on either of these. We'll place our axioms on the weak preference, the weak inequality symbol, right? But every axiom on the weak inequality, the weak preference, will have implications for these other preference relations, okay? Some of the properties may carry over. So in one of the problem set exercises, you have to sort of do careful proofs of that. For example, one of our axioms is going to be that the weak preference ordering is transitive. And that property, it turns out, given these definitions, carry it over to strict preference also, and indifference also, and also even some combinations of strict preference and indifference. Okay, but now, for now, focus is on weak preference ordering. So what are the axioms of the theory. Okay, there'll be 4 axioms, and later we'll add a 5th, right? The 4 axioms will give the main result, which is called the preference representation theorem. And the 5th will put some additional structure. So first axiom is the completeness axiom. Okay, what is it saying? It's saying that for any pair of consumption bundles, the logical quantifiers are very important. Okay, when we say for all, that means one thing. When we say there exists at least one, that's a different thing. So pay attention to the logical quantifiers. So the completeness axiom is saying that give the consumer any 2 consumption bundles, which means any 2 points from the positive orthant of the Euclidean space, Rn plus. One of these 2, at least one of these 2 has to be true. Either the consumer will tell us that x1 is, I weakly prefer x1 to x2, or I weakly prefer x2 to x1. And sometimes the consumer can say both. We are not ruling that out. Of course, when the consumer makes both of these statements, then that means the consumer is indifferent between the bundles x1 and x2. That's how we have defined indifference. So what is this saying? What this is saying is that the decision maker, the consumer, knows her mind. The decision maker doesn't confront a choice situation and a simple binary choice situation and just scratches her head and says, I don't know, I'm confused, I can't make up my mind. That is being ruled out. Now, of course, in real life, sometimes we face these choices. Yes, you get 2 fantastic job offers, high salaries, great perks. You may be torn for a while. Which one should I choose? You get admission to Harvard and Stanford, and you think, well, tough choice. I don't know. I'll have to sleep over it. However, to build any kind of rational choice theory, we have to assume completeness. There's an option. Okay. If we allow for our agent or consumer to not really be able to rank these 2, then, well, we can't say what she'll choose. She doesn't know herself. What are we going to say? So completeness is absolutely necessary to build a theory of choice. Shaunak.
Sir, what I wanted to ask was, when you say or both, does that not mean confusion? Like when the user or the consumer doesn't know what to choose, when she's indifferent between the 2, so that's not confusion, right?
That's not confusion. That's right. That's just indifference. That's the consumer telling us that I don't care. The 2 bundles are equally attractive to me. Okay, which is completely different from the consumer saying, I can't really make up my mind. I'm confused. Sometimes I lean this way, sometimes I lean that way.
So basically, the first axiom says that both the bundles can be compared, like
yes,
with each other, right? Okay,
that's right. Yeah. Nilava?
So what is the difference between consumer choice and consumer preference? Or are this the same?
No, preference is something in your mind, okay, how you rank things. In principle, you may not choose your favorite alternative. You may choose your second favorite, third favorite.
Okay, so we make choices from our preferences.
You may or may not make choices based on your preferences, right? So, I mean, there are kind of subtle issues about that. There's a very famous article by Amartya Sen called "Rational Fools." Let's talk about it later. Yeah, I mean, we are just starting out, so
Thank you, sir.
Complicate it too much at this point. So right now we are talking of mental orderings of the various things you can choose from. Now, what you'll actually choose is an additional assumption. And obviously, I'm giving away no spoilers when I say that at the end of all these axioms, which characterize the preferences of the consumer, the theory will get launched by assuming that the consumer chooses the best possible alternative. Right? Now, anyway, we'll get into trickier issues later. Second axiom is transitivity. And I described transitivity a while back, so let's not belabor the point. Any three bundles, essentially transitivity is ruling out preference loops or cycles. Okay. Again, so this is like saying that, if there are three channels on TV, there's a news channel, there's a movie channel, and there's a sports channel, and you have to choose between them. If your preferences were that you prefer the movie to sports, sports to the news, and news to the movie, then you have a preference loop. Then you have intransitive preferences. The problem with intransitive preferences, once again, is that it does not translate into a well-defined best choice. When you have a loop like that, whatever alternative you choose, whichever channel you switch, there's always a better channel. So basically, you end up cycling between channels. And we, as economists, observers, social scientists, we won't be able to predict what your choice is going to be. So it is essential to assume transitivity. Is it a reasonable assumption? Is it in the sense that, is it empirically relevant? I mean, do people most of the time have transitive preferences? Well, maybe, let's hope so. Let me just throw in a caveat. Sometimes when you're talking about group preferences, depending on how you formulate group preferences, they may end up being intransitive. So there's a very famous example. I don't know if you guys have seen it in undergraduate, the Condorcet paradox.
Yes, sir.
Okay, so.
Sir, can you please explain? I'm not aware.
Okay. Okay. So suppose there are three roommates in a dorm. Yes. They have one TV. They have to decide which channel to watch. Let's say, so the channels are sports, news, and what was the third I said? Movie, of course. And three people, A, B, and C. And how do they rank these things? A ranks sports as number 1, news as number 2, movie as number 3. B ranks news as 1, movie as 2, and this is the third. And C puts movie on top, followed by sports, followed by news. Okay. Now, the very fact that I can write these rankings means that they have transitive preferences. Each individual has transitive preferences. But then, because there's one TV, they said, okay, let's come up with a social preference ordering, right? Let's create a ranking for the three of us as a group. And then, so A makes that suggestion, and B says, Okay, fine in principle. How do we do that? How do we aggregate our preferences into a group preference? And C, who was silent for this while, comes up with a brilliant idea. C says, we'll do pairwise majority voting. Okay, first we'll take vote between sports and news. Whichever wins will be preferred to the other for the group. Then pairwise voting between news and movie, and finally between movie and sports. Okay, so if we compare sports and news and take the vote, which will win?
A is preferred to be.
Two people prefer sports to news, right? A prefers, C prefers. So sports is preferred to news. Between news and movie, the first two guys prefers the news. So news is preferred to movie. And between movie and sports, movie is preferred to sports. Okay. Now, the group preferences, are they transitive?
No, sir. They're cyclic.
No.
You have a cycle, yes? Now, you could say that, well, maybe pairwise majority voting was not a good way to try and aggregate these preferences. Maybe, there are other ways that can be suggested. For example, just to mention one, you could use what is called the Borda rule, right? Borda rule says take people's ranks that they assign, add them up. So sports, all the ranks add up to 6. News also 6. So Borda rule basically says that get all the ranks coming from different individuals for an alternative, add up those ranks, and whichever alternative gets the lower aggregate rank is placed on top. The one which gets the second lowest sum of ranks gets the second to the top spot, and so on. Now, if you apply that here, you end up with indifference between sports, news, and movie. Okay, so the problem seems to be resolved if you move away from pairwise majority voting to the Borda rule. Okay. However, I can cook up an example where the Borda rule will also maybe, will run into, some other problems. May not be a violation of transitivity, but some other nice property will be violated. Now, this example, this 3x3 example, was first given by Condorcet, who was a French mathematician many centuries back, 18th century, I believe, no, 19th century. And he said, okay, there's a problem here. And he came upon it not as an abstract exercise. He was trying to come up with voting rules for the French Academy of Sciences. And Borda was his intellectual rival there. So he came up with a different rule, and they were apparently didn't like each other much. So they fought over their rules. Much later, Kenneth Arrow proved that the problem that we encounter in this example is much more general. So any aggregation rule you come up with, any formula you want to apply to aggregate individual preferences into a social preference runs into a problem in the sense that it violates some desirable property. If you manage to satisfy all the desirable properties, the rule will end up violating transitivity. Okay, it won't be a proper preference ordering. So why did I make the digression? I made the digression to drive home the point that transitivity is a non-trivial assumption as far as its empirical relevance is concerned. In a modern society and economy, there are many decision makers are large bodies. They're like firms which have shareholders and board of directors who have to make choices. We have parliaments. We have, various NGOs, what have you. So organizations consisting of many people with perhaps conflicting preferences have to somehow decide what course of action to choose, what kind of choices to make. And when we are talking of collections of individuals, transitivity is tricky, is the point. But at this point, we will accept it, yes? And if you're building a theory of individual choice behavior and individual preferences, then transitivity perhaps is not, a bad assumption to make, even from an empirical perspective. Yes, Ravleen.
So, as you mentioned in the previous example, that if we focus on individual preferences, they are transitive. If we see pairwise, they are not transitive. And if we see that the rule you said of averaging, it is indifferent. So, how do we judge or explain the axiom of transitivity? Which form to focus on? Which formula to look upon? Do we look them individually or pairwise or as a group?
No. Okay.
Adding up the preferences.
So what I just said on, here is a digression. Here I'm talking of group preferences and the question of what kind of rule do we apply to aggregate group preferences from individual preferences, right? And there I showed you that if you aggregate them through what looks like reasonable rules, like pairwise majority voting, you often end up with intransitive group preference orderings. Now, that's a digression. At this point, let's come back to the main track. And here I'm saying that we'll just assume transitivity. Here, aggregation is not an issue because we are talking of individuals. We are trying to build a theory of individual choice behavior, and their aggregation is not an issue. But the reason I mentioned it is if you want to sort of extend this, when you say, okay, I want to understand the choices of big corporations with their board of directors voting over the policies. I want to understand the choices of parliaments and how parliaments or legislatures will respond to changes in the circumstance. And there, assuming transitivity can be problematic, is what I'm saying. But we are not in that area, right? So this is a warning label that when you analyze organizations, their preferences may not be transitive, depending on how they add up the individual perspectives to a group perspective.
Okay, sir. Good.
Ravleen? Oh, no, that was Ravleen. Okay, two more assumptions. Axiom 3 is kind of a technical sounding assumption of continuity of preferences. So here is one way to write it down, but there are other ways to write it down, which are given in the bullet point below. They are all equivalent ways of stating the axiom of continuity. Let me explain what this somewhat terse description means. Let me explain by drawing a picture, and explaining things is always easier if we assume two goods, okay, but the principle is more general. So there's a two-good world. Quantities are x1 and x2. And suppose we are comparing two sequences of bundles. How should I write this? So now we're talking of vectors. So I consider one sequence of points. It's the X sequence. This is a vector, bold, right? And these are superscripts. X2, X3. And it's a convergent sequence. It converges towards some limit point X. There's another sequence in this space that we are looking at, another sequence of bundles. That's the Y sequence, Y1, Y2, Y3. And this second sequence converges towards a limit point Y. Okay, converges meaning that every successive element, in the distance from the point Y of every successive element gets smaller and smaller, and in the limit goes to 0. And suppose we know that the ith element of the first sequence and the ith element of, ith element of the second sequence and the ith element of the first sequence, they satisfy this. So yi is strictly weakly preferred to xi. Okay, true for all I. That symbol means for all. Our continuity axiom says that that ranking also has to hold for the limit points. So y, the limit point of the first sequence, should be weakly preferred to x, limit point of the second sequence. This property has to be true. That's what the continuity axiom is saying. Okay, I'm coming to questions now. So you can't have that, you know, we are trudging along successive elements, right? We're comparing y1 to x1, y2 to x2, y3 to x3, and so on. And all along, we find the y element is better, at least as good as the x element. But suddenly, when we hit a limit, it reverses. That is not being allowed to happen. That is being ruled out. Okay? The same property has to extend to the limit. Now, this is also equivalent to, and I won't prove this, this axiom can also be stated differently in the following manner. Let me define a set, the weakly preferred set. So I'll look at a reference bundle. Let's call it X0. Okay. What is this set? This set is the set of all points which are weakly preferred to X0. Okay, the weakly preferred set. And this is a set of all points such that X0 is weakly preferred to each of them. So weakly better and weakly worse sets. So another way to state the continuity axiom is to say that these two sets are closed sets, meaning they include their boundary points. Okay. Yes, Sakshi.
So I have a notational doubt. When we in the previous case that we've discussed, the diagram above, here there are two codes, x1 and x2, and each of the yi and xi are a bundle of those two goods, right?
Yeah.
So the series that we've made are actually a series of bundles of these two goods, and they're of two different individuals. Is that what it is? X and Y too?
No, same individual.
Same individual. Okay.
Right.
Thank you, sir.
So I was actually, you know, I realized this room for confusion just as I was going to draw this picture, but I moved ahead nevertheless. These x's on the axes are quantities of individual goods. These x's here are vectors, bundles. So are the y's. It's slightly less than ideal notation here. Okay, Shubham.
Sir, my doubt was kind of same that like x1 x superscript 1 is like a bundle of two vectors or two goods like
Two here in this
x1 and
picture,
x2.
in this picture, two goods, in general n goods.
Okay, so sir, one more thing, and you were talking about limit. When limit, you were saying that the successive distance between the two vectors would keep on decreasing. Sir, can you please explain
No,
that?
I didn't say that. I said that the distance between a point in the sequence and the limit point, that distance goes to 0. That's a convergent sequence.
So,
not the distance between successive points, but the distance from, so this distance xi minus x, this goes to 0 as I goes to infinity. That's a convergent sequence, and any point which has this property that the sequence, that's called the limit point. Yeah.
So we are just saying that as I goes to infinity, x and xi are one and the same thing in a way, approximately.
X and Y are one and the same thing.
Xi and xr are
almost. So xi is getting arbitrarily close to
close
x.
to x.
That's right.
Yes. Thank you, sir.
That was Shubham, was it?
Yes, sir. Yes, sir.
Orko?
Sir, why do we need this axiom of continuity?
We'll see that. I mean, hold some patience. If I tell you at the beginning who the murderer is, you won't read the detective story. So I'll have to, you'll see. Okay, I'll tell you, the butler did it. We need those, eventually we'll rescue utility functions, and we want those utility functions to be continuous functions. So no wonder we need to make the continuity axiom. That'll guarantee that. Yeah. Priyanka.
So in the above diagram, you said that while we were seeing the individual bundles, so they were going together, but while going to the limit value, something reversed. Can you please repeat that point? I couldn't get it.
So here's a violation of the continuity axiom. Let's look at it from the negative side. So suppose I have found, I've collected all the data on this consumer and her rankings, and then I'm analyzing it. And I found this, that, I can construct two sequence of bundles. All along the sequence, the X bundle is preferred to the Y bundle, okay? But when we get to the limit points of the sequences, it exactly reverses. Now, what did I say? Let's say, all along the sequence, the Y bundle is preferred to the X bundle. But once we hit the limit exactly, it's the other way around. X is now preferred to Y, or strictly preferred to Y. That will be a violation of the continuity axiom.
Got it, sir. Thank you.
Okay.
Sir.
Yes.
Sir, can you explain the sequence of bundle with some numerical examples?
No, that will be just too tedious. Why do I,
I mean, sir, the distance is getting smaller and smaller. This is not getting clear.
Okay, let's, these are kind of things which I think better sorted out in tutorials, right? So I'm not dismissing your question, but let's reserve that for tutorials. Okay, what the mathematical and graphical concept is. What is the correspondence between them? Let me put that on hold. Okay, you should. So one of the things in the tutorial about the tutorials is that there's the script is not sort of baked in. So you can ask your questions, you can clarify your doubts from your tutor. So I encourage you to take some of these, because if I have to deal with all of that, I'll be nowhere close to finishing the syllabus. So raise the question with your tutor. Yeah. Okay. Who's next? Who did I ask? Is it Shonak?
Sir, I have a question. The question is, you came up with another explanation that it's closed under the next part. Can you please explain that once more? Like, is this one?
Yeah. So what is a closed set? Anybody, you guys familiar with these concepts?
Yes, the limit point is in the set itself. So
right. So the set I'm talking about is, one is the weakly preferred set, one weakly better set, one is the weakly worse set. So take any reference bundle X0, right? Both these sets are defined with respect to some reference point or bundle. So for any reference point, you can ask, what are the other points which have the property that they're all weakly preferred by the consumer to axiom? Okay, that is what this set is. Typically, I'll even draw a picture. I'm jumping the gun a little bit, but the concept of indifference curves will come, and many of you are familiar with it. So basically, it's the indifference curve and everything above. If you know what an indifference curve means, some of you may not, but I'll define it in a moment. So that's the weakly better set. Okay, and the weakly worse set is the stuff below, with the property that the indifference curve belongs to both of these sets if preferences are continuous. All right.
Okay, so I got it. Yes, I got it.
Yeah. So I won't prove it, but these two definitions are equivalent. Yeah. Shishir?
Yes, so that was exactly my question, that how are these two statements equivalent exactly? Like even not just in a logical way, but in an intuitive way, how are they equivalent?
You try to prove it. Okay. Some of these things, it's best how these things are kept open. So if something intrigues you, try to prove it yourself. That'll be a valuable exercise, and we can discuss it later. Okay, for now, let me just make the assertion. Okay, let me get back on track. Rishi, very quickly.
No, sir, my doubt was also the same about the two explanations.
Okay. Last axiom is strict monotonicity. So that says, I think this should be rephrased slightly. Notice this is not a curly inequality. Okay, this is basically saying that if you compare these two bundles, the first bundle weakly dominates the second bundle. Okay, meaning that the first bundle has at least as much of each good as the second bundle. Allows for ties, allows for equality, but for no good does the first bundle contain a lesser quantity. So suppose the two bundles look like that. Then the consumer has to weakly prefer X1 to X2. Okay, and although it's not entirely made clear here, we'll also assume that if X1 is strictly higher than X2, so you have strictly higher of each good, then the preference will have to be strict, essentially, right? So the more the merrier. This leaves open the possibility that if you increase the quantity of only one good and not the others, then, or only a subset of the goods and not the others, the consumer may still, it may not be a strict preference. So that is being allowed. But the crux of it is that, colloquially speaking, the more the merrier. Everything is a good. The axiom of continuity, the intuitive explanation, if you want to kind of think about it intuitively, what it's basically saying is that you cannot drastically alter the consumer's assessment of a bundle by tinkering only very slightly with some of the quantities. Okay, two bundles which are very close in quantity are also very close in preference. That's one way to understand it. Okay.
So could you explain strict monotonicity once?
Strict monotonicity says that if I compare these two vectors, and this first vector has weakly more of each good compared to the second, then the consumer weakly prefers the first bundle to the second.
Okay, sir.
Sir,
Yes.
so like you just said that if we increase the quantity by just a little amount, then the preferences are just a little bit better off. Sir, is this the same definition that we use for local non-satiation?
No.
Is it different than that?
Yes.
Okay,
Local
sir.
non-satiation is basically monotonicity.
Because if sir, I don't remember correctly the definition of local non-satiation, but it was like we can always find a point in the vicinity of a point that is just strictly better off than that original point. Maybe it is a
Local
definition.
non-satiation means that, you know, sometimes if you add quantities, you get worse off, essentially, right? Or
Okay, sir.
not get better off, even if you are increasing the quantity of everything.
Okay, sir.
So that is being ruled out over here.
Okay, sir. Okay, sir.
Excuse me, sir.
Yes.
Sir, strict monotonicity is also like saying that average is preferred to the extreme, right, sir?
No, that is
not like
convexity. That will come later.
Oh, okay.
So again, you have to sort of, in your study, you have to kind of think back. These things are a bit abstract and dense, so you have to look at it closely, re-look at it closely. Okay, let me jump ahead to the final result, which is the centerpiece of this, and then today's lecture will stop. Yes.
So I have a
Shonok, let me put you on hold. Just, you know, let me just finish it because I'm running out of time. Actually, I have run out of time, but as usual, I steal a little bit of your lunchtime, so I'll do that. Okay, and I'll come back to your question. Now, what is the consequence of making these assumptions? It has a very interesting consequence and a very useful consequence, actually. Here's the preference representation theorem. It says that if all these four axioms are satisfied for some consumer, then there exists a continuous increasing function u, okay, which represents these preferences, meaning that whenever one bundle is weakly preferred to another, this alleged function, this function which the theorem is claiming exists, will generate a higher number for the more preferred bundle. So that's the sense in which it represents preferences. Okay. In other words, the function will be a nice, this alleged function is kind of a measuring tape, if you will, right? It assigns one number to every bundle, and that number becomes an index of preference, if you will, right? Higher numbers represent more preferred bundles. Now, first of all, if the set of alternatives was finite, okay? Suppose we had 10 alternatives, you know, instead of this whole Euclidean space and all the points in it, there were only a finite number of alternatives. Then this theorem, should we be impressed by this theorem? We shouldn't be, because then it's very easy. Whichever is the most preferred bundle of the consumer, you give it, let's say, the number 10. The second favorite is given the number 9. all the way down to 1. So if there's a finite number of alternatives, we can just use integers to describe, to create a scale where more preferred bundles are given bigger numbers. So it's non-trivial only because the set of points available to the consumer is not only infinite, it's not countably infinite. If anybody, let me not get into the details of that, but it's basically, this whole Euclidean space. And one of the famous mathematical results is due to Cantor, is that you don't have enough integers to assign to all the points on a real line or in a two-dimensional Euclidean space, and so on and so forth. So anyway, so it's not at all obvious at the outset that we will be able to construct such a function. So that's the sort of deductive meat of the theorem, that we'll be able to construct it. But let me explain. I'll do the proof next time, or it'll be in your lecture video. But why are we even bothering with this theorem? Didn't we sort of criticize utility functions, Alfred Marshall's utility functions? Didn't we say that those are nebulous things which we can't measure? We don't want anything to have to do with it. Well, the thing is, in the old cardinal theory, choice theory, utility functions were assumed to exist. Okay. In this theory, what is assumed to exist is preference orderings. That's what is assumed to exist in the consumer's head. And this is telling us we can always, provided the preference ordering satisfies these properties, the 4 axioms, we can always think of or analyze the problem as if the consumer is maximizing some utility function, as if. The role of as if assumptions is it goes back to an article by Milton Friedman called the methodology of positive economics. So Friedman gives the example of theories from physics and biology. So for example, grass, the thickness of grass depends on which part of the ground gets more sunlight. Okay. The areas which get more sunlight have thicker grass. So grass grows as if it's maximizing, I think, sunlight available per blade, something like that. Similarly, in physics, you have in classical optics, there's something called Fermat's principle, which says that in going from point A to point B, light follows that path which takes the least time. Now, if point A to point B passes through different media, for example, A is in water and B is in air, right? And in between, there's a transition from water to air. Light has different speeds in the different media, okay? Now, if Fermat's principle is true, then the path of light will follow a particular trajectory, and it will, you can show that it satisfies the laws of refraction, for example. Many of the laws follow from that. Anyway, it has been confirmed that you could describe the path of light from point A to point B by this principle that it minimizes travel time. Now, if we took that literally, we would think, light is in a hurry. It has to get to the office, or it wants to rush us home to see the match. Of course, that's absurd, right? Light doesn't have a mind. So all of those theories have to be interpreted as, it is as if nature is behaving in a way which can be described by some maximizing principle. So it is the correspondent thing over here, okay? That if we go and ask these consumers, what's your utility function, they'll look at us like they're crazy. But what this theorem says is that logically, we can describe their preferences and then later their choices with the device that it is as if they're maximizing some utility function. It's in the as if sense. So that's the difference with classical theory. Classical theory says, it's, some function exists in their heads. Yeah, it's in the as if sense. So it's the utility function is a device which is useful to us, not to the consumer, but to us who's studying the consumer. Okay. Now, why are we bringing back utility? Because later, as we move on, I'm jumping ahead a little bit, but we'll see that eventually, when we say that the consumer tries to pick her most preferred bundle among the things that she can afford, stated that way, the problem is very difficult to analyze and get results out of. But if we can formulate the problem as one of maximizing some nice continuous function, then we have all kinds of powerful mathematical techniques that can be brought to bear on the problem, and we can derive powerful results. So that's why this is a very useful device. What this theorem does is that it gives a nice conceptual foundation to the utility function instead of assuming that it exists right at the start. Okay, so next day, in the next lecture, I will sketch out the proof of this theorem, and also another theorem which basically says that utility functions are not unique, right? The same preferences can be represented by a whole class of utility functions, and then we'll see what kind of theory we can develop from that.
So the next lecture is a recorded one, right?
That's right.
Okay, sir.
Okay.